This video will describe how to create or find the images and describe them that are created by the reflection of light on spherical mirrors. When we locate an image, we draw something called a ray diagram. The ray diagram illustrates three principal rays of light. The first ray that we draw is the P ray, and it is parallel to the principal axis. So the purple line is parallel, and when it hits the mirror, it is going to diverge or converge on the focal point. The second ray we draw goes through the focal point. It's called the F ray. The F ray goes through the focal point, hits the mirror, and always bounces back parallel to the principal axis. The third ray is the C ray, and it goes through the center curvature. And because it's going through the direct center of the mirror, it bounces back and forth and doesn't get bent or in any way. So let's look at a convex mirror. Remember that convex mirrors diverge light. They always make a virtual image. That image is going to be upright, and it's going to be located behind the mirror. Excuse me. Alright, so the object is drawn in on the principal axis in front of the convex mirror. The P wave goes from the top of the object to, let me just get this bigger so you can see it. The P wave goes from the top of the object parallel, and when it hits the convex mirror, remember convex mirrors diverge away from the focal point. So if you take a ruler and line up this point with the focal point, then you can draw the reflected ray and dot back to the focal point. The C ray goes from the top all the way through, aimed at the curvature, the center curvature. So that's just a line. And you need to dot it going back behind the mirror because there's no real light there. And then finally the F ray goes from the top of the object, pointing straight at the focal point, and when it hits the mirror, it bounces parallel, and you dot back that parallel way. Notice that they all three intersect in one location. So this is where the image is going to form. Notice that it's upright, that it's virtual, cannot be projected. Remember that the focal length of a convex mirror is negative because it diverges light. It always makes a virtual upright image. Notice that the image is behind the mirror where there's no light, versus a real image that would form over here. So let's look at a concave mirror. Turns out a concave mirror can make either a real or a virtual image. If the object is very far away from the focal point, when you draw the P wave and it converges through the focal point, you draw the F ray, it goes through the focal point and then bounces back, you see that they intersect below the principal axis. They also are real rays of light. So this is a real image. The image distance is on the same side or in front of the mirror as the object is. It's a positive image distance versus a negative image distance for a virtual image. Also, real images are always going to be upside down or inverted. If the object is much closer as we approach the focus, the image is still upside down and bigger, but it's still a real image. This is kind of what's happening when you use this as a magnifying mirror. It turns out that if the object is a lot closer than the focal point, it's going to form a virtual image. So if we want to kind of look at these two images that are being formed, we've got two triangles here. We've got the height of the object and the distance the object is to the mirror. We've got the height of the image to the distance the image is to the mirror. It turns out that these are similar triangles. So these ratios are going to be similar to each other. We can use that information to write two equations. The first one is the mirror equation. 1 over the object's distance plus 1 over the image distance equals 1 over the focal length. Where dou is the distance to the mirror and the object, di is the distance from the mirror to the image, and f is the focal length. Remember that if we're dealing with a converging mirror, convex mirror, f is 1/2 of the radius of curvature. It's a positive number because it converges light. But if f is negative, we're dealing with a convex mirror that diverges light. In general, if you have a convex mirror, it always forms an upright virtual image. But a concave mirror, it depends where the object is. If the object is anywhere outside of the focal point, it forms a real inverted image. If the object is outside of the focal point, it forms an upright virtual image. So when we use the lensmaker or the mirror equation, we also can derive from the similar triangles that the magnification, which is how big the image is compared to the height, is equal to negative di over dou. So in general, focal length is going to be positive for concave mirrors because they converge light. Focal length is going to be negative for convex mirrors because they diverge light. M is going to be positive for upright images, and M is going to be negative for inverted images. The image distance is positive in front of the mirror and negative behind the mirror. The object distance is positive in front of the mirror and negative behind the mirror. So here's kind of another chart that might be a good visual organizer for you. If you have a concave mirror, if dou is greater than f, dou, di, and f are all positive. If you have a concave mirror and dou is less than f, then the image distance will be negative because you're making a virtual image. And the convex mirror always makes a virtual image, and it always has a negative. Here are a couple of examples. A concave mirror has a radius of curvature of 20 centimeters and is used to view a 3 centimeter tall stamp placed 10 centimeters away from it. Describe the image. So I know this is a concave mirror which converges light. So the focal length is a positive half r. So half of 20 is 10, it's positive 10 centimeters. The image distance is 3 centimeters. And we're going to look at the object distance. So 1 over f equals 1 over dou plus 1 over di. So 1 over 20 equals 1 over 3 plus 1 over dou. So if I rearrange this, I'm going to take the inverse of 20 and subtract off the inverse of 3. That's going to give me a decimal. That is not the object distance. I have to take the inverse of that number to get the distance. The distance is negative 3.52 centimeters. So negative 3.52 centimeters means that it is located behind the mirror, 3.52 centimeters. And it's negative, so it's a virtual image, and virtual images are always upright. What if it's much further than the focal length? So let's change this problem so that the object is 30 centimeters away. The focal length is still positive 10 centimeters. The image distance is now 30 centimeters. When we do our math, we get positive 60 centimeters. Positive means that it's in front of the mirror and that it's real. And because it's real, it'll be upside down. What if we change the mirror and keep the same numbers? So now we're dealing with a convex mirror. A convex mirror diverges light So its focal point will be negative 10 centimeters. The image distance is still 30 centimeters. When we do our math, we're going to have negative 20 minus 30 minus 30, which is going to give us negative 0.083 centimeters. Taking the inverse, we get negative 12 centimeters. Negative means it's virtual and it's behind a mirror. Upright, because it's virtual. So I've just noticed that I had a mistake here. So what we're going to do is, when you see the actual PDFs of this, the focal length will be 20 centimeters and the curvature will be 40 centimeters. Because it looks like I made a systemic error where I did not plug in the actual focal length. So you want to plug in the focal length, and the focal length, I'll just change it to be 20 centimeters, which means the radius, the curvature is 40 centimeters. And I apologize for that problem.